Hello everyone, welcome to a fresh lecture on Wavelet Transform 2. So I am Dr. Anirban Dasgupta and here we will talk about the discrete wavelet transform. So what is DWT? It's the discrete counterpart of our CWT and this is used for efficient signal decomposition and analysis. But what is the difference? The main difference is that in CWT we had our scale and translation which is continuous. So DWT will discretize the time and scale parameters, that is you will have fixed values for A and B, and similarly it will decompose your signal into approximation and detailed coefficients at different scales using the choice of the wavelet, and this is implemented through a multi-level filtering process. So here concepts of your multi-resolution or multi-rate signal processing will be used, and that is what I am talking about. So it provides a multi-resolution analysis of the signal, that is it is breaking the signal into both low frequency and high frequency components at different scales. So to calculate the DWT of a signal x of n, what we will do is we will pass it through a series of filters. So first the samples of the signal x of n will be passed through a low pass filter, and let us say Gn is our low pass filter, or I would say Gn is the impulse response of the low pass filter. So this is how you will do the low pass filtering, that is convolution, and this is what we get, and I call the output as y low of n, and the signal will also be decomposed simultaneously. Why simultaneously? Because this result is independent of the first operation, but here I will do it for a high pass filter. Now if you can relate this to the concept of filter bank, this is very much similar. So in filter bank what we were doing, we were taking a signal and then splitting it into different filters which were responsible for a specific band of frequencies. So here consider that this filter bank consists of two filters, one is a high pass filter and one is a low pass filter, and we are filtering the signal simultaneously like this. So now the low frequency output is kind of telling you how the signal behaves approximately, whereas the high frequency content is giving you the finer change in the signal. Now this is very often used in image processing because it is visually very easier to appreciate this detail and approximation thing. So if you know painting, or if painting is a hobby of yours, you know that you use different kinds of brush, and that is a very good analogy I give to my students, that if you use a thick brush, so say you want to paint a scenery and there is a sky region and there are some grass regions. So you will use your thick brush, and the sky regions you will paint it very casually to get it overall bluish look, and similarly the grass regions or the mud regions you will use approximately green or brown kinds of shades, and that gives a holistic overall view of the approximation of the region, that the region is overall blue or overall greenish in nature. And then you can use the thin brush for making details. Details means the grass, there are some subtle variations in intensities. So that is the high frequency or detailed coefficients, or in the concept of wavelets. Not only in the concept of wavelets, in general image spatial frequency, those are the high frequency components, those details in the picture where you use the thin brush. So these two filters are related to each other, they are forming a filter bank, and this is called a quadrature mirror filter bank. So why quadrature mirror? Because the response is related to each other and they are exactly splitting the frequency content into two equal halves. And since now the frequencies are halved, why halved? So if I say 0 to pi, this is the frequency content of the signal. See, it may not be like this, there can be high frequencies lot present as well, but I would say that, so let me take a different color. So, say this is the region. If it is an ideal filter, it would take up only this region. This is my low frequency part, but real filters will somehow have a smoother response. So, this is my low frequency observation of the signal, which is Y low. And similarly, if I take another color, let us say blue, if I say this other region, so this is pi, this is 0, and this region, so if you say this region is the high frequency content. So, in other words, this is capturing the low frequency range, while this is capturing the high frequency range. So, my bandwidth is half. So, we can easily reduce the sampling rate, or in other words, we can half the samples. So, since the filter output is downsampled by 2, we can write this equation, which is the equation of downsampling, and pictorially we see that these are the responses Gn and Hn, and then we downsample by a factor of 2 and we get the approximation and detailed coefficients. So, this is what I showed is called level 1 decomposition. Now, similarly, I got the level 1 coefficients from the high pass filters, but my approximation or low pass can be further analyzed. So, I can have another level which is called level 2, and here I do the same thing considering the output of my first level, which I call the approximation coefficients, into further application of the same low pass and high pass filter, and again this will again reduce the bandwidth by 2, which I can again downsample by 2, and this gives me the high pass detailed coefficients in level 2. And again, if you go one stage higher, we can get level 3 and so on. So, this is like a binary tree where you are getting a split, and this is representing a subspace with a different time frequency localization. Why different time frequency localization? I will show you pictorially. And this tree is basically now a filter bank. We already discussed filter bank in the multi-resolution, multi-rate topic. So, we see that at each level the signal is decomposed into low and high frequencies. So, this is what I was talking about. So, due to this decomposition process, we see that at every stage the frequency content is halved, then another stage frequency content is halved. Let us say this is my frequency range in the analog, for example, f of n. So, first level I will reduce it to 0 to Fn by 2 and Fn by 2 to Fn. So, it is halved. In the second level again it is this Fn by 2 is again reduced, because this high frequency I am saving as my detailed coefficients. Only the low frequency part I am again sending to another pair of filters, which will again divide it into 2 bands, Fn by 4 to Fn by 2 and 0 to Fn by 4. Again in level 3 we again split it into 2 halves, 0 to Fn by 8 and Fn by 8 to Fn by 4. So, this is the signal length should be multiple of 2 power n, 2 power something, where n is your number of levels. If you do not have, you can pad your signal with zeros. So, for example, if a signal has 32 samples, so 32 means 2 power 5. So, effectively we will have 5 levels. So, here I have shown 3 levels. So, first level, so it will be split into 16 and 16. This 32 is split into 16 and 16. Say these are my detailed coefficients which are taken out, and these approximation coefficients are again split into 8 and 8 in this. So, this is level 1, level 2 I do this, then I extract this detail, and then this approximation is again subjected to high pass and low pass, which will give me 4 4, and this is my level 3 decomposition. This is 4 4. So, here I have shown up to level 3. So, this detail again I can store, and this approximation will again be subjected to 2 2, and this detail. So, this is level 4, and the last is I get 2 in level 5. So, this is 1 1. So, this is how this signal is split in wavelets, and each time you see that the scale is different. So, some properties of our DWT is that first is it is providing us a multi-resolution decomposition, and the signal is represented at different scales or levels of details. So, in level 1 we get some amount of detail, in level 2. So, this is low pass with respect to level 1 or these coefficients, but this is high pass with respect to the upper half. So, it is relative kind of a thing, and overall if you see, this is kind of a mid frequency thing, and every detail coefficient is a high pass counterpart in that level, but with respect to the previous level it is a lower frequency band. So, this is computationally more efficient than CWT, and naturally because CWT you are allowed to choose any A and B, but here in DWT we are carefully selecting our A and B. Also the decimation. So, since the frequency or bandwidth is reduced to half, so we are downsampling the signal in time domain, so that each stage we get half the number of samples, like 32 got reduced to 16 16, 16 got reduced to 8 8, and so on. And the last thing is orthogonality. So, this transform is often orthogonal. Often orthogonal means most of the wavelet bases are orthogonal. Sometimes there are some bases which are not directly orthogonal, like this V and W which I said, the scaling functions and wavelet functions may not be directly orthogonal, but they can be bi-orthogonal, like at different scales they can be orthogonal, and that is the bi-orthogonal wavelets. But in general you assume that because of this orthogonality property, the signal can be perfectly reconstructed from its wavelet coefficients, or in simple words, so we get 16 such coefficients. In Fourier also DFT, if there are n number of samples in the time, we got n number of samples in the frequency. Here also if we have n number of samples in time, we get n number of samples in the wavelet domain, but the reconstruction is again level wise. So, you have to design not only the analysis filters, but also the reconstruction filters. So, if you are using this wavelet toolbox like PyWavelet in Python or in MATLAB, you will see that for each kind of wavelet like Haar or Dobitsch's, there is a set of this analysis function, and there is a set, or you can say you will find the name decomposition wavelets or decomposition filters, and in this reconstruction you have reconstruction filters. So, there are a lot of applications of this DWT, and primarily two applications which most of us are using. One is JPEG 2000 image compression. You have heard of JPEG 2000. JPEG 2000 is a very nice image compression algorithm which is better than the JPEG algorithm, which uses DCT, discrete cosine transform. And similarly H.264. So, this latest videos which are upscaled and looks very nice in color or appearance are using this H.264 codec, which uses this discrete wavelet transform, as compared to the MPEG codec, MP4 codec, which was using the discrete cosine transforms. Then in denoising wavelets are very nicely used. You see lot of research papers, many people are using wavelets specifically for biomedical signals, and they are getting really good results. So, noise are usually high frequency components. So, usually if you see the detail coefficients, and if you can do some kind of thresholding, you can see that you can very nicely denoise such signals. And then feature extraction. So, in many machine learning algorithms, this instead of using the raw signal or raw image to the classifier, you can use the wavelet components as features into the classifier, and they perform better. And this is useful in tasks like texture analysis and speech recognition. So, to compare between the CWT and DWT, So, CWT, if we talk about the time frequency resolution, so it is a fine time frequency representation, because the scales and your these translations are continuous, whereas these are given at specific scales. So, that is the continuity in scale and frequency, whereas this is discrete in scale and frequency. And naturally, this will be computationally expensive because of this redundancy, whereas DWT is computationally much efficient because of using this downsampling thing. And similarly, for data redundancy, the CWT is highly redundant and DWT is non-redundant, because we are downsampling. So, we are not keeping extra samples which are unnecessary, and reconstruction in CWT may not be always perfect without this downsampling, because we will get unnecessary information, but in DWT exact signal reconstruction is possible. So, this is used in high precision time frequency analysis, where you need very precise localization kind of a thing, whereas this is in general good for signal analysis unless you need that level of precision, that exact time, where if you that even miss with 0.01 seconds it would be a big disaster, then probably CWT is a better option, but otherwise DWT is pretty good for most of the signal analysis and compression as well. So, let us take an illustration and say this is a signal, simple signal, and these are our Haar wavelets. So, this 1 means basically I am just summing them, convolving with a kernel 1 means I am just summing the window, and 1 minus 1 means I am just taking the difference of the two consecutive samples, and that is why Haar is so simple to understand, because it is just doing sum and difference. Now, this thing you also observed in our 2-point DFT, which was used in FFT. And then why this division by square root of 2? Now, this is just to ensure that the energy is conserved in both the time and the wavelet domain or frequency domain. So, how do we do the level 1 decomposition? So, as I said, we need to convolve this. Now, if we convolve this, we will typically get the same length, and what happens is basically then, as I said, that we will be downsampling by a factor of 2. That means, we will pick up alternate samples, and hence the length will be half, because after convolving the length will be kind of same, then we will downsample to make it half the length. So, here you can clearly see that. So, what I am doing? So, x0 plus x1, x2 plus x3, but wait a minute. So, if I have this and if I do a convolution, shouldn't it be this plus, then this, then this, and then this, and then this? But you see here that even if I do this problem, that 1 plus 1 divided by root 2, so I will get a value which ultimately I will downsample and discard. So, what is the point in computing this? So, I will not compute these, I will just compute the sum of the consecutive values, and then I will not do the sum of 1 and 1, I will just keep it, because that will be anyway downsampled. So, I will then do 1 and 2 and then 2 and 1. So, that is written here, this and this, and this is the final low pass or approximation coefficient. So, you see here that the signal length is halved here. So, downsampling is already considered here, and that makes this efficient. Similarly, in the high pass, I am just taking the difference of the two values. So, x0 minus x1, x2 minus x3, x4 minus x5. Here also I have not done something like x1 minus x2, because even if I calculate this is useless. I will downsample and discard this. So, I need not do this operation, and this is what I get, and again the length is 3, which is half of the original length 6, and this is our first level decomposition of that signal, and these are our approximate value, which is telling you that 133, which means this is how the trend of the signal is, that it is slightly increasing and then getting a level. whereas the detail is telling that what is the change. The -1 is showing that there is a decrease, and then there is a decrease again, and then there is an increase. So, this is capturing the changes in the signal. So, in time also I am localized that the two values how are they behaving, and then in frequency also I am saying that whether it is going high or low within that two values, and that is Haar wavelet for you. So, take an example of this signal which is having a length 8, and if we do a first level decomposition of this. So, this is my low pass filter or scaling filter, and this is my high pass filter or wavelet filter. So, here just to show you I have done the convolution, and this is what I get, and then I will discard the alternate sample. So, I discard this, and similarly I discard the alternate samples. So, I am downsampling, and this is the first level approximation and detail coefficient. You see the length is halved. So, this is having length 8, this is having length of 4. Now, again you might be wondering that this should be 8 plus 2 minus 1, which should be 9. Now, I have used the same length without padding, so that the length remains 8 itself. So, even if you get 9, that will also be kind of, you can discard it. So, then again here in the second stage or second level, what we will do is we will now take the approximation coefficient obtained in the previous operation, and then I will repeat it. I will multiply with the low pass and high pass, not multiply, convolve, and I get this, and again I do the decimation, and I get the next level approximation and detailed coefficient. I request you to do this either manually or using a computer and verify the results and repeat it with different values of x, so that this concept will be clearer to you. And similarly, the third level decomposition, and I repeat the process and I get these two values, I decimate and I come to single value. Now, here I cannot further break because this is having only one element for the detail and approximation. This should be A3 and D3. So, here you see that since there were 8 values, which is 2 power 3, so we could decompose to 3 levels. Now, similarly we can reconstruct the signal by doing the reverse process. So, first we will combine the third level, then second level, and then reassemble all the levels. So, that is it from this lecture. Thank you very much.